Look up. There is a star hanging in the dark, and it looks calm, steady, almost bored with its own existence, the way old things sometimes are. You could watch it for 100 nights and it would tell you nothing was wrong. No flicker, no warning, just light, arriving the way it always has. But that light is not proof of anything. It is a rumor, a very old rumor, about a place you cannot see. Because somewhere behind that glow, in a chamber no telescope can reach, a war may already be lost. And the strange, uncomfortable truth at the center of this story is simple. A star can be dying while it still shines. Its death can be underway right now, tonight, while its face shows you nothing but calm. We are going to go there. Not physically, no ship could survive it, but with understanding. We are going to travel inward, past the light, into the actual machinery of a star's final hours. And by the end, you will never look at a steady star the same way again. Every star alive is fighting a war it eventually loses. On one side, gravity. Relentless, patient, pulling every particle of the star inward, trying to crush the whole thing down to a point. On the other side, pressure, generated by the heat of nuclear fusion in the core, pushing back outward with equal force. For most of a star's life, these two forces are in a standoff. Physicists call it hydrostatic equilibrium, a clinical name for something almost dramatic. A decades or millennia-long truce between collapse and explosion, held in place only because the star keeps generating enough heat to hold gravity off. Think of it like a crowd pressing against a set of doors, and something on the other side pushing back just hard enough to keep them shut. As long as that pressure holds, nothing moves. The star simply shines. That balance is what you're seeing when you look at a normal star. Not peace, a standoff. And standoffs eventually end. A massive star doesn't burn one fuel. It burns through a sequence of them, like a fire that, once it exhausts one kind of wood, is forced to reach for something harder to ignite. First, hydrogen fuses into helium. When the hydrogen runs low, the core contracts, heats further, and starts fusing helium into carbon and oxygen. When that runs low, the core contracts again and fuses those into neon, then oxygen, then silicon, each stage shorter than the last, each one demanding more heat and pressure than the one before. By the time a massive star is fusing silicon, it is no longer burning for millennia. It is burning for days, then hours. The star, from the outside, looks almost identical to how it looked a million years earlier. But internally, it is racing through the final chapters of its life at a pace that would terrify it, if stars could feel terror. And then it reaches iron. Hey guys, quick one before we continue. YouTube just told me that over 90% of the people watching this video right now are not subscribed to this channel. 90%, that's almost everybody. You're here, you're watching, you're enjoying the content. And that means everything. But if you want to see us keep making documentaries like this, the only way to show that is to subscribe. Hit the subscribe button. Hit like, share this video with one person. We are pushing hard to reach 10,000 subscribers before 2027. And honestly, with your support, we can get there way before that deadline. This channel is just getting started. Be part of the story. Now, let's get back into it. Iron is where the story turns. Every fusion reaction up to this point has released energy. That release is what held gravity back. But fusing iron does not release energy, it costs energy. Iron sits at the peak of nuclear stability. Forcing it to fuse further is like trying to squeeze more work out of a battery that is already fully drained. So the core stops fighting. There is no new heat to hold the doors shut. And gravity, which has been waiting this entire time, finally gets its opening. The iron core begins to contract. As it does, temperature and density spike violently. High-energy photons, the same light that should be a source of pressure, begin to tear the iron nuclei apart instead, breaking them back down into lighter particles. This process is called photodisintegration, and it is, in effect, the core cannibalizing its own support structure to buy gravity even more room to work. At almost the same moment, something else happens deep in that crushed material. Electrons are forced to merge with protons, converting them into neutrons and releasing a flood of nearly invisible particles called neutrinos. This is electron capture, and it strips away one of the last sources of outward pressure the core had left. The pressure produced simply by electrons refusing to be squeezed any closer together. Two support systems are failing in the same instant. The core, which took hundreds of thousands of years to form, is now losing its final defenses in a matter of moments. What happens next does not unfold at a stellar pace. It unfolds at a pace closer to a car crash. In a fraction of a second, the core's outer material comes rushing inward at a significant fraction of the speed of light. A region the size of a planet compresses down toward the size of a city. The collapse doesn't stop until it hits a wall, not a physical wall, but a wall built out of the fundamental resistance of matter itself. Once the core reaches nuclear density, the same density found inside an atomic nucleus, neutrons packed against neutrons finally refuse to be compressed any further. The infalling material slams into that wall and rebounds. In an instant, something new exists at the heart of the collapsed star. A proto-neutron star, an object so dense that a teaspoon of it would outweigh a mountain. From here, one of two futures unfolds. If conditions are right, the rebound helps trigger a shockwave that eventually tears through the rest of the star. If the mass collapsing inward is simply too great, there is no rebound powerful enough to stop it, and the newborn neutron star itself continues to collapse, silently, completely, into a black hole. Either outcome is a point of no return. But before either one becomes visible to the outside universe, something else has already escaped. Neutrinos are strange messengers. They interact with matter so rarely that trillions of them are passing through your body right now, and you will never notice. That same property, the thing that makes them almost impossible to detect, is exactly what makes them special in a collapsing star. While light struggles to fight its way out through the dense, chaotic material of the star's interior, neutrinos slip through as if that material barely exists at all. The result is one of the most counterintuitive facts in all of astrophysics. In a nearby core collapse event, the burst of neutrinos produced by the collapsing core can reach Earth hours before the visible explosion does. In 1987, when a star collapsed in a neighboring galaxy, detectors on Earth registered a sudden pulse of neutrinos roughly 3 hours before astronomers saw the light of the supernova itself. The universe, in other words, can whisper the truth in neutrinos long before it shouts it in light. And this is the heart of the mystery we opened with. Why does the star's surface not immediately reflect what's happening in the core? The answer lies in something almost mundane: distance, and how light behaves inside dense matter. The outer layers of a massive star are enormous, layers of gas so thick that photons generated deep inside don't simply fly straight out. They scatter, get absorbed, get re-emitted, and scatter again, bouncing through the star's interior for a journey that can take far longer than the collapse itself takes to happen. So the light reaching the surface, and eventually your eyes, was already on its way out long before the core's final crisis began. The star's brightness tonight is, in a very real sense, an old signal, a photograph taken before the disaster, still being delivered after the fact. This is the dissonance at the center of the documentary's title. The star can be actively dying, its core already collapsed or collapsing, while the light leaving its surface still carries the signature of a healthy star, because that light left on its journey before any of this began. Brightness, it turns out, is not a live broadcast. It is a delayed transmission. Back at the core, the outcome is still being decided. The rebounding shock wave, born when the collapse hit the wall of nuclear density, doesn't automatically succeed. As it pushes outward, it loses energy tearing through infalling material and breaking apart atomic nuclei in its path. In many simulations, the shock stalls. It runs out of momentum before it escapes the star. For the explosion to happen at all, that stalled shock needs to be revived. Current research points to several possible mechanisms working together. Neutrinos, streaming outward from the newborn proto-neutron star, depositing just enough energy behind the shock to reignite it. Turbulent, boiling motion in the material behind the shock, which helps trap that neutrino energy where it's needed. And magnetic fields in rotation, which in some stars may add an extra push. If revival succeeds, the result is a core collapse supernova, an explosion that can, for weeks, outshine the entire galaxy the star lives in. The outer layers are blasted outward at extraordinary speed, forming an expanding shell of hot, glowing debris that astronomers can track for months as it fades. If revival fails, there is no explosion. The collapse simply continues, uninterrupted, until the star's remnant crosses its own event horizon and vanishes from the observable universe entirely, a death with no fireworks at all. That second outcome, the quiet one, deserves its own moment because it may be more common than early models assumed. Some stars, particularly the most massive ones, appear to collapse directly into black holes without producing a bright supernova. Astronomers have gone looking for stars that were there in earlier surveys and simply vanished from later ones, with no explosion ever recorded. Candidates for exactly this kind of silent collapse. It is a genuinely strange idea. A star, one of the largest and most luminous objects in a galaxy, disappearing from the universe not with a flash, but with nothing at all. No light, no warning beyond that early neutrino pulse. Just absence, where something enormous used to be. Whichever path it takes, the star that existed before this moment is gone. What remains depends entirely on how the story ended. A successful supernova leaves behind an expanding remnant, gas and dust laced with newly forged elements, spreading outward into interstellar space. At its center, if the collapse stopped at nuclear density, sits a neutron star, an object roughly the size of a city, yet more massive than the Sun, spinning in some cases hundreds of times per second. If gravity won completely, what's left is a black hole, not a hole in space, but a region where matter has been compressed past the point where anything, even light, can escape its gravity. And scattered through the wreckage of either outcome are the elements the explosion helped create. Iron, sulfur, calcium, gold, elements heavier than iron that fusion alone could never produce, but that the extreme conditions of a collapsing, exploding star can. Some of that material, the calcium in your bones, the iron in your blood, the oxygen you're breathing right now, very likely traces back to an event exactly like this one, in a star that lived and died long before the Sun ever formed. This is the strange gift hidden inside stellar death. Destruction, on this scale, is also how the universe manufactures the raw material for everything that comes after, including us. It would be dishonest to end this story pretending everything about it is settled. The broad outline, collapse, neutron star or black hole, and in many cases an explosion, is well supported by observation and decades of theoretical work. But the precise physics of exactly how a stalled shockwave gets revived, why some collapses explode and others don't, and what role turbulence, rotation, and magnetic fields each play in specific stars, is still an active area of research. Supercomputer simulations have gotten dramatically better at reproducing successful explosions in recent years, but the fine details, which stars explode, which quietly become black holes, and why, remain an open question astrophysicists are still working through. That uncertainty isn't a weakness in the story. It's an honest acknowledgement of where the edge of current knowledge sits, and a reminder that even something as fundamental as how massive stars die is still being actively studied. So go back to where we started. A pinpoint of light in the dark sky, steady, seemingly untroubled. Now you know what that steadiness can hide. You know that the photons arriving in your eyes tonight may have begun their slow escape from that star's interior long before its core ever began to fail. You know that, for some stars, the truest and earliest warning of the end wouldn't come as light at all. It would come as an almost undetectable flood of neutrinos, passing through the Earth, through you, completely unnoticed, hours before anything visible changed. The star you're looking at may be perfectly fine, or its core may already be gone, already collapsed, already a neutron star or a black hole, while its outer layers are still finishing the performance the star's interior wrote for them years, or centuries, before the ending was decided. That is the quiet unease at the center of this story. The visible universe is not a live feed, it is a delayed one. And somewhere out there tonight, a star is very likely dying while it still shines. Its final act already underway, its light still telling you everything is fine, because the light simply hasn't caught up to the truth yet. Brightness was never proof of safety. It never will be. It is just the last thing to know.